Hello, everyone. My name is Arik Grimberg. I'm a doctoral student at the Technion in Israel, and I'm going to present mine and my supervisor's work, Idit Kedar, on intermediate value linearizability, IVL, a new correctness criterion for quantitative objects. But what are quantitative objects used for? Well, in the world of big data, which govern ads, what ads you see on the internet, and how Google does your autocomplete, what's generally underlying are statistical summaries or statistical algorithms or approximation algorithms. For example, data sketches. These are generally updated using batch counters or batched updates. And such data sketches are quantitative objects in such that they support two operations, an update and a query, where the update returns just an ACK and a query returns a value from a totally ordered domain. These systems, these big data systems are scalable in such that they are generally in large distributed systems, each system running a multi-core server using shared memory. So what we want to do is leverage this multi-core system for parallelism, but this introduces an error, first from the parallelism and in the underlying approximation algorithm. So the question is, how do we analyze this error? Well, let's first think why we use linearizability. Linearizability was used so that we can analyze an algorithm in a sequential setting, and this analysis carries over to the concurrent setting. Well, that's what we aim to do with IVL, to define a correctness property that a sketch or an algorithm can satisfy in the sequential setting or in the concurrent setting. Then we can analyze it in the sequential setting, and this analysis carries over to the concurrent setting. That's what IVL does. It allows us to analyze the error of approximation algorithms sequentially, which is much more simple. And this error analysis carries over to the concurrent setting. Okay, but let's first kind of understand and motivate where IVL is coming from. So as a simple example, let's look at counting events, counting people connecting to servers, to be more exact. And our current setting has two servers, A and B, and there is a supervisor which decides whether or not another server is needed. And it decides so by checking whether or not there are more than 50 people connected to the servers. So each server has a local counter, which holds how many people are connected to it. For example, the server reads the counter in server A, which returns 24. It reads the counter in server B and returns 18. Thus, it can see 42 people are currently connected to the servers, which means we don't need another server because it's less than 50. What this example is coming to show is a distributed counter. So there's a counter that's distributed amongst A and B, or all the servers, and the supervisor wants to read the value of this counter, and it does so by querying each server. Okay, but let's see what happens in the real world, so to speak, when things start happening in parallel or concurrently. So let's say 6 people get batched together to be updated onto server A. So they happen to have connected at a close time, and server A decides to update its local counter with it to show these 6 new people. So the supervisor decides to query the servers again to see if a third one is needed. It reads the counter on server A. Server A hasn't finished updating its local counter, so it returns 24. Server A then finishes updating its local counter. People start connecting to server B, and server B decides that it needs to update its local counter with 10 to show that 10 more connections have happened. The supervisor reads the counter on server B finishes updating its local counter, and therefore returns 10 more than the previous 18, returning 28. The supervisor then sees that 24 plus 28 is 52, 52 is greater than 50, and a third server is needed to handle the stress of all the clients. Let's consider the time series of this simple example. We have a batched counter starting at 42, ending at 48, and we have a read happening concurrently to an increment of 6 followed by an increment of 10. And the question that arises is, what are the allowed values that the read is allowed to return? What are the values that the read is allowed to return? Well, under linearizability, it can either return 42, which is the value before the increment, 48 in between both increments, or 58 after both increments. We can see that in our simple example, the read returned 52. Therefore, this execution is not linearizable. But the question we ask is, what's wrong with 52? I just wanted to know if I was going to start up another server or not. And at 58, I'm going to start up another server. So I just kind of saw that I need to start another server up a tiny bit earlier. So what's wrong with 52? Or if I would have read 48, what's wrong with that? Or at 48, I don't need to start up another server. So what's wrong if I would have read 43? What's wrong with any of the numbers between 42 and 58? Is anything inherently wrong with them? The intuition behind IVL is that no, there is nothing wrong with any of the numbers that are bounded between two legal ones. And it allows the return of, in this example, any number between 42 and 58. Well, that's the intuition and informally how IVL works. But let's define it formally. So in order to define IVL formally, we first need to define some properties, or we need to define some formalisms that we're going to work with. So the first one is skeleton histories. And the skeleton history is the skeleton of a history. What we basically do is we take the history H and we replace the return value of every read with a question mark, basically saying we haven't decided what this read is going to return yet. Okay, so in our example, instead of read returning 52, it now returns question mark. But from skeleton histories, we need some way to go back to, well, real histories or something we can work with. To do that, we define the operator tau, which together with a sequential specification, we replace these question marks with the correct values that would be returned in the sequential specification. So in the sequential example, the counter begins at 42, increment 6, and read return question mark. Well, what does it return? Let's apply tau using the sequential specification, and the read will return 48, which is 42 incremented by 6. So the tau operation takes any sequential skeleton history and returns a history that is in the sequential specification. Okay. What we can now do is we can define linearizability using skeleton histories and the operator tau, and we can arrive at a definition that is equal to the definition of linearizability that exists. So the way we define it is we take a concurrent history H and we say that it's linearizable if there exists a linearization H prime of its skeleton history such that the return value of every read operation in our original history H is equal to the same read value, the return value of the same read in tau of H prime. Okay, so we basically look at the return value of every read, and if it's the same as in a sequential specification, then it's linearizable. And this is very intuitive as to why it's equal to linearizability, because if the execution is indeed linearizable, we can take its linearization, say that's equal to tau of H prime, we look at its skeleton, and thus we arrive at a linearization of the skeleton of the original history H, and vice versa. So we can see that this is equal to linearizability. But let's run through an example to really drive the point home and truly understand how to work with skeleton histories in tau. So let's take our simple example from before and see whether or not this history is linearizable, which the spoiler is that it's not, but let's prove that it's not. So the first thing we do is we consider the skeleton history. So we first have the read return question mark instead of 52. We then want to show that no such linearization of its skeleton history exists as required. So let's consider all the linearizations of its skeleton history. In the first one, the read occurs before both increments. In the second linearization, the read occurs between both increments. And in the third linearization, the read occurs after both increments. So we now have all the possible linearizations of the skeleton history, where the read occurs before the increments, the read occurs in between the increments, and the read occurs after the increments. Well, now we need to see what the return values are of these linearizations of the skeleton history. So let's apply tau. So you can see that in the first linearization, the read returns 42, which is the value of the counter before both increments. In the second one, 48, which is the value of the counter at 42 incremented by 6. And then the last one, it's 58, which is the value of the counter at 42 incremented by 6, incremented by 10. We now need to see, does any linearization of the skeleton history satisfy the requirement by the definition? Well, our original read returned 52, so let's see if any of them are equal. First one's 42, that's not equal. Second one's 48, that's not equal either. And the third one's 58, that's not equal either. Thus, we have seen that no such linearization of the skeleton history exists as required, thus proving that this concurrent history is not linearizable through the notion of skeleton histories and the operator tau. So when defining linearizability, we took a single linearization of the skeleton history. To define IVL, we take two possible linearizations. we say that a concurrent history is IVL if there exist linearizations H1' and H2' of the skeleton of H, such that the return value of every read operation in H is bounded between tau operating on H1' and tau operating on H2'. What this essentially means is that the return value in a concurrent history is bounded between two legal ones allowed under the sequential specification. Okay, well, let's see if our simple example is IVL or not. And the spoiler here is that it is. So let's first take a look at all the possible linearizations of the skeleton history after applying the operator tau. We now need to bound the original return value. The original return value is 52, so we can bound it by 48 and 58. Now that we've found two linearizations as required, we can now say that the concurrent history is indeed IVL. So as a short interim summary and a spoiler for the rest of the presentation, we've currently presented IVL for non-randomized objects, deterministic non-randomized objects, in which for quantitative objects. So a quantitative object is one that the query returns a value from a totally ordered domain in order to create the bounds that needed. And there are multitudes of quantitative objects, sketches, counters, and so on and so forth. We'll show that IVL is cheaper than linearizability inherently in some cases. It will also prove our main theorem in that it preserves the error bounds of a sequential object, which is why we wanted to define IVL in the first case. And we also prove that it's a local property, so it's composable. So we can think of every object by itself instead of thinking of the whole system at once. A nice side effect of IVL is that it's also adaptive to contention. So when there's no contention, IVL is equal to linearizability. What this means is that when there's no contention, an execution under IVL adheres to the sequential specification. This is a bit different than previous relaxations of linearizability, which allow for even a sequential execution to differ from the sequential specification up to the allowed amount under the relaxation. So this is a nice property because it means that when everything's happening sequentially, then I know that what the return values that I'm getting are as defined in the sequential specification. However, when there's a lot of contention, when my execution is highly concurrent and things are happening in parallel quite a bit, IVL allows for flexibility, basically allowing any return value that's bounded between the minimum and the maximum values of that read's execution time. Okay, so it allows any of the values bounded between the minimum and the maximum. That's a lot of flexibility. So what we have is that it's adaptive to contention. When there's no contention, we're very rigid. We require to remain within the sequential specification. And when there's a lot of contention, when we're in a highly concurrent setting, IVL allows to more fluid return values. Okay? But what we want is to define a correctness criterion for approximation algorithms or data sketches. They're randomized objects, so we need to first define what IVL is for a randomized object. Well, what is a randomized object? Or what's the sequential specification of a randomized object? Well, the sequential specification of a randomized object becomes non-randomized once it's instantiated with a coin flip vector. So once I've decided on the coin flips for this execution, I now have a sequential specification that is defined and rigid. Following this, we can now get a distribution over the sequential specifications. So we have a distribution over the possible coin flip vectors, and defining each sequential specification using a coin flip vector allows us to define a distribution over sequential specifications. This is essentially a randomized object. We have a distribution over sequential specifications. Our definition of IVL for randomized objects is such that the return values in H are bounded as required by the IVL for every coin flip vector C. So it's IVL if once we've decided on the linearizations of the skeleton history, every coin flip vector C maintains the bounds. So now that we've defined IVL for randomized objects, we now need to show that the error analysis of data sketches in general it follows over from the sequential setting to the concurrent setting. But in order to do this, we first need to define, well, what is an approximation algorithm? What is a data sketch? Well, we capture this notion in epsilon delta bounded objects. The sequential specification, the sequential definition for epsilon delta bounded objects is such that a query returns an approximation of an ideal value. such that with probability at least 1 minus delta over 2, the approximation is greater than or equal to v minus epsilon. And with probability at least 1 minus delta over 2, the approximation is less than or equal to v plus epsilon. What this means is that with probability at least 1 minus delta, the approximation returns the ideal value with an error of at most epsilon. So with probability at least 1 minus delta, the error is at most epsilon. And there are many examples from the data sketch world, such as the k-minimum values, the quanta sketch, Campbell sketch, and so on and so forth. Most of the sketches, or all of the sketches, are epsilon delta bounded objects. The main theorem that we prove in our paper is that a concurrent IVL implementation of a sequential epsilon delta bounded object is a concurrent epsilon delta bounded object. The proof follows quite nicely from the definition of IVL. So consider some query Q that returns some value, some approximation in H, and consider some coinflip vector C. IVL promises a linearization H1 of the skeleton of H, where Q returns an approximation such that the approximation is less than or equal to the approximation in H1. A linearization H2 of the skeleton of H, where the query returns an approximation such that the original approximation is greater than or equal to the approximation in H2. But H1 and H2 live in the sequential world. So for H1, with probability 1 minus delta over 2, its approximation is less than or equal to v plus epsilon, which means that our original approximation is less than or equal to v plus epsilon. And with probability 1 minus delta over 2, the approximation in H2 is greater than or equal to v minus epsilon, which means that our approximation is greater than or equal to v minus epsilon. So what we have is the approximation in the concurrent execution is with probability 1 minus delta, it has an error of at most epsilon. Okay? What this means is that a concurrent IVL implementation of a sequential epsilon delta bounded object is itself epsilon delta bounded. So let's recall why do we use linearizability? Well, we use linearizability because it's indistinguishable from an atomic variable. So what we can do is analyze how the algorithm behaves when an atomic variable in a sequential setting, or analyze what happens in a sequential setting. And if the algorithm is linearizable, then we know that this sequential guarantee carries over to the concurrent setting. And that's exactly what IVL does for epsilon delta bounded objects. Epsilon delta bounded objects have sequential guarantees. They're error bounds with probability, they're probabilistic error bounds. And IVL maintains that this error analysis carries over from the sequential setting to the concurrent setting. So IVL is sufficient for epsilon delta bounded objects. Okay, well, that's very nice. And we can show that in some cases, indeed, IVL is more efficient, but is it inherently more efficient than linearizability? Well, in some cases, it is. As an example, let's consider the batch counter from the simple example from before. So a batch counter has two operations, an update, which gets a non-negative value, and a read, which returns the sum of all the non-negative values passed to the updates before it. That's a sequential specification. And let's show or propose an algorithm, an IVL algorithm for solving the batch counter problem. So we use a shared array with n indices, so v1 through n. An update on process I updates its index, so vi gets vi plus v. And a read simply sums over all the array, reading it in a non-atomic way. So why is this IVL? Well, let's consider the sum returned by the read. The sum returned by the read must be no less than the sum of the array at the beginning of the read. So if no updates were happening, it would return that. But because updates have non-negative values, the sum is at least the sum at the beginning. And it can be no greater than the sum at the end of the interval of the read, because I can't predict the future. I don't know what's going to happen. So the sum is basically bounded between the beginning of the read interval and the end of the read interval. So we have an IVL batch counter. So considering the time complexity, the read has an order of n. I need to read the whole array. And the time complexity of an update is order of 1. Well, what about in a linearizable batch counter? Well, what we prove in the paper is for any linearizable implementation of a batch counter, from single write to multi-reader registers, the time complexity of the update operation has to be at least n, order omega of n. And we show this proof using a reduction from a batch counter to a snapshot. It also needs a time complexity of read of omega n, but that's the same as an IVL, so we don't write that here. But what we show is that for any linearizable implementation of a batch counter, an IVL implementation is inherently cheaper. So IVL is sometimes inherently cheaper than linearizability. To conclude, I've presented IVL, which we see as an intuitive correctness criterion in which values observed in concurrent executions are bounded between two legal ones with respect to linearizability. I've shown the idea of the proof of our main theorem that IVL implementations of randomized objects with bounded error have themselves bounded error. As an example in the paper, we also show a count-min sketch, and we present an efficient way to get its approximation, which is much cheaper than using a strong linearizable implementation. We've also shown that it allows for cheaper implementations, sometimes inherently, than linearizability. Thank you.